All right, welcome back to the Kitchen Research Group. I'm very pleased to tell you about a recent paper that was published in the Journal of Physical Chemistry C on cyclic steady-state simulation and waveform design for dynamic programmable catalysis. This has been a collaboration with Carl Laird, who is the optimization expert, and our student Carolina, who did all of this work. And this was published as part of a special Festschrift for Jens Norskopf. So Jens, congratulations. This paper is on properties of volcanoes and how to use them to accelerate reaction rates. And so we thought it would be a fun addition to your Festschrift. Okay, in a nutshell, we can get higher rates of reaction in a catalyst if we can operate dynamically. So this green line over here is a volcano, and what it shows is the rate as a function of a binding energy of a molecule A on a surface. And if you operate statically, if you have a fixed binding energy, then this green line tells you what the maximum catalytic rate, the turnover frequency is that you can expect. And you have a region over on the left where you're limited by the rate of surface reaction, on the right where you're limited by desorption. And there's a peak here that is called the Sabatier peak that is often considered the highest possible frequency that you could expect from a class of materials that follows this reaction mechanism. The idea with dynamic catalysis, though, is there are ways of modifying the binding energy. Perhaps you could strain a surface periodically or change the pressure, shine light, put in an electric field, something like that. And if you can switch back and forth to the left and the right side, then you switch from one rate limiting step to another, and you can get a much higher reaction rate out of this. Now, an open question has been, what's the best waveform and how do you find it? And that's what we spent time in this paper trying to figure out. All right, so the reaction system we looked at was a very simple one. It's molecule A adsorbs on the surface to make A star. It reacts to form B, and then that can desorb. And we can modify the binding energy of A star and B star by some mechanism. You can read in the paper what some of those mechanisms are. And we have on the right a set of ordinary differential equations that are mass balances on each species and a site balance at the bottom. So to figure out what's happening in this system, what we have to do is have an equation for the binding energy as a function of time. And then that gets plugged into the set of differential equations, which you have to solve to get the solution. A typical way is to set an initial condition on the surface concentrations, plug that into these equations, use an integrator, and forward integrate until you get cyclic steady state. What we did instead was to create a boundary value problem, and this is an approach that's been used by some others, including Paul Downhauer and Keverkidis, where they made a formulation in the boundary value, where instead of integrating forward in time, we recognize that at cyclic steady state there are boundary conditions that the functions, the surface concentrations, everything on the one period has to be equal in the next period, and that allows us to change the way we approach the problem in a fundamental way that makes it compatible with optimization. So instead of trying to integrate forward in time, we simply solve a boundary value problem, and that lets us get one limit cycle very efficiently. It turns out to be way faster than trying to solve the IVP. So I show on the left in figure A here the time evolution of a turnover frequency if you start out with the surface being empty. Then you have to integrate a bunch of steps to fill up the surface, and then you see these oscillations that occur over time, and then you have to run it long enough to be sure that it's at cyclic steady state, and that's time consuming. You can see by the very sharp change in concentrations that it's quite stiff, and so this is a challenging problem. In the middle, in C, we compare the IVP in red, time to solution, to the time required for BVP, and you can see we're orders of magnitude lower in most cases with the BVP approach, so it's much faster to get to a solution. And you can see on the right what some of these solutions end up looking like. The orange line might be a square wave that we can oscillate a binding energy on. The blue line is the corresponding turnover frequency that comes out of the simulations, and then we can integrate that to get an average. One thing we found, others have seen this too, but it's easy to see now that the optimal waveform depends on the specific reactions. And so if we look at different ratios of forward and forward reactions in that mechanism that I showed you, if we have this ratio that's much less than 1, then we need a small duty cycle where you spend less time in the upper state than you do in the lower state. If you have a very high ratio over here, it's just the opposite. You need a longer duty cycle where you spend more time in the high state. And you can see this is what the turnover frequency looks like as a function of that duty cycle with the red dot at the very top. So that efficient solver allows us to work out all kinds of examples. This is brute force optimization if you want, by enumeration. We also can employ things like scipy.optimize, .minimize for finding these kinds of solutions as well. We've taken a few steps towards more flexible waveforms. Ideally, we would have a very flexible waveform, but that still is a challenging optimization problem, and we learned a lot of things just by trying something as simple as a sum of 2 Gaussian pulses. And when we find a superposition that kind of looks like a square wave, we find that to be better than these 2 separate ones. This is a little bit tricky to figure out overall. There are a lot of parameters that go into this, including the amplitude. And this double pulse here has twice the frequency of this one, and we know that frequency matters as well. So it's in general a tricky question to ask, what do you even mean by the best waveform, because there are interrelated factors with frequency and amplitude and other things. Nevertheless, we have a framework now that it's easy to try these optimization problems and start exploring multiple different parameters. So while a square wave might have 2 or 3 parameters, the duty cycle, the intensity, and maybe one other, over here we have multiple parameters. We have the center of the peak, the width of each peak. Those are separate variables that are adjustable to start playing with. And as we get more and more of these, you just get a higher order or higher number of parameters to be optimized. All right, so in summary, this work shows that, and this was known from Paul Dauenhauer's early work in the field, that dynamic catalysis can lead to orders of magnitude increase in catalytic rates for the reaction system studied here. We developed a BVP approach, boundary value problem to modeling that was way faster than the initial value forward integration and more amenable to optimization. And we showed how to apply the optimization to find the best waveforms, at least within some constraints of the best square wave or best pair of pulses for maximizing the catalytic rate. The article is open access. You can find it online and read it. Link is in the description. And there's a very extensive set of Jupyter notebooks in the supporting information that document all of the code we used, all of the studies that we did. You can run them in Colab, and everything should be smooth and operatable for you if you're interested in learning about this. So thanks for listening, and